In this lesson, we give some examples of applications of functional equations to probability and statistics. We start with the problem of maximum stability, looking for families of distributions such that when we obtain the maximum of independent random variables in the family, we obtain a new random variable in the same family. Next, we look for families of priors such that the posteriors for a given likelihood belongs to the same family. We continue with sums of a random number of random variables. We also identify the families of distributions such that when adding independent variables of that family, we get a sum which is in the same family too. Finally, we identify families of bivariate distributions with linear regressions and conditionals in location scale families. As indicated, we start with the maximum stability problem.
We can use functional equation, of course, in statistics, for maximum stability. We want to find families of distributions such that the maximum of independent copies of this family will give you another distribution that also belongs to that family. And then we can write this in terms of functional equation.
Assume two independent random variables x and y with cumulative distribution functions f and g respectively. Then the cumulative distribution function of c, the maximum of x and y, is the product of the distribution functions f and g. An interesting problem consists of finding families of distributions such that the maximum of a set of independent variables in that family also belongs to that family. Interesting particular cases are the extreme value families of distributions, Frechet, Gumbel, and reverse Weibull. If we want x, y, and z to belong to the same single parameter family f, the functional equation in expression 1 must be satisfied, where the function m gives the value of the new parameter as a function of the previous parameters a and b. The solution of this equation is the one indicated in expression 2 on the top of the slide, where f is a cumulative distribution function, h is invertible, and both are arbitrary functions. In addition, function m is an associative function because it is of the form of the already known solution of the associativity equation. The reader should understand why this could be expected. Equation 1 is a particular case of the functional equation in the next slide with general solution in expression 5. Making there m equal to n equal to f and h equal to the product x times y in the next equation, we obtain the solution 2. It is also of interest the case of stability with respect to minimum operations. In this case, we get the functional equation 3, where g is equal to 1 minus f, that is, a survival function instead of a distribution function. Interesting particular cases are the extreme value reverse Frechet, reverse Gumbel, and Weibull distributions. In this slide, we present the generalized autodistributivity equation in expression 4, a very general equation that can be used to solve other functional equations that appear in this lesson, as particular cases of it. The general continuous solution of this functional equation is given in 5, where the involved univariate function must satisfy the indicated conditions. Next, we deal with the problem of Bayesian conjugate distributions.
You can do the same for Bayesian conjugate distribution. We say that a distribution is conjugate when the prior and the posterior belong to the same family, but we also know that the posterior is the product of the likelihood times the posterior, times the prior, sorry. So the likelihood is L of x theta, and the prior is f of theta eta. That is the posterior. If I want the posterior to be in the same family of the prior, this posterior should be written as an f function, the same as the prior, times of theta, and the new parameter should be a function m of the sample x and the prior parameter eta. This is a functional equation that can be solved, and then you get all conjugate distributions.
Assume that the random variable x belongs to a uniparametric family with the likelihood function L of x, and theta is the parameter. And assume also that theta has an a priori probability density function f, that is, it belongs to a uniparametric family with parameter eta. It is convenient to have prior and posterior distributions in the same family because it simplifies a lot the calculations. If we force the a posteriori distribution to belong to the same family as the prior, Bayes' theorem gives us expression 6, where the function m gives us the value of the new parameter as a function of the sample value x and the prior parameter eta. Functional equation 6 is a particular case of equation 4, with n equal to f, and h is the product x times y, but the arguments of f are reversed. If we can guarantee the regularity condition in the generalized autodistributive equation, the general solution is the 1 in 7. I recommend the reader to replace 7 into 6 and check personally how the functions k inverse and k cancel out so that 6 holds. Our following problem is the sum of a random number of identically distributed random.
You can also consider what happens with you when you add independent copies of distributions that belong to the same family, r equal to x1 plus x2 plus xn, but n is random, it's not a fixed number, it's random. Then we know by generating function, probability generating functions, that the probability generating function of r, the sum, is equal to g of n and then g of x. So you can write a functional equation and solve
variables. In practice, we have cases in which we have sums of a fixed number of random variables, but sometimes the number of terms of the sum is not fixed but random. For example, the total sales of a company are the sum of the sales of a random number of clients. Next, we deal with the problem of sums of random variables when the number of terms is random, but all of them belongs to the same family of distributions. Let R be a random variable such that it is the sum of n random variables, with n a random variable 2, as indicated in expression 8, where n is a discrete random variable with probability generating function g sub n, and the x sub y with I ranging from 1 to n, are independent and identically distributed discrete random variables with probability generating function g sub x. Then the probability generating function of R is given by the expression at the bottom of the slide. This is a well-known result from probability theory. Then the most general uniparametric family of random variables that can be generated by the sum 8 using uniparametric families for x and n, a random variable, satisfy the functional equation in 9, where f, g, and k are the probability generating functions of the families associated with n, x, and r respectively. Equation 9 is a particular case of equation 4, and then, if the regularity conditions are satisfied, we have the generally continuous solutions in the box area. If we want the f, g, and k to be probability generating functions, the conditions at the bottom of the slide must be satisfied. In the particular case in which the random variables x, n, and r belong to the same uniparametric family, they need to satisfy the functional equation in 10, which is the transformation equation, which under some regularity conditions leads to the general solution in 11. In addition, for f to be a probability generating function, we must have the extra conditions indicated. The reader should replace 11 into 10 and check personally that the function k inverse and k and n inverse and n cancel out so that equation 10 holds. Equation 11 is very useful to provide some solutions of this equation 10. Our next problem is the reproductivity problem. In this section, we characterize reproductive families of distributions. We consider two cases, 1 and 2 parameter families. We say that a family of random variables is reproductive if the sum of independent random variables of the family belongs to the family, that is, if the family is closed under sums of independent summands. From probability theory, we already know that the characteristic function of the sum of two independent random variables is the product of the characteristic functions of the summands. Thus, the reproductivity property for uniparametric families can be written as the functional equation in 12, where the characteristic function f is a complex function of two real variables. The function g is a real function of two real variables a and b, which tells us how the parameter of the sum can be obtained as a function of the parameters a and b of the two random variables being added. This equation, taking into account that the characteristic function can be written as in the first expression at the top of the slide, where f1 and f2 are the modulus and the argument of f, respectively, can be written as in 13. Since the first of this equation is the same as the one used in the maximum stability problem, we can write its solution as in 14. The second equation is a particular case of 4 with h equal to x plus y and f equal to m equal to n equal to f2. If all regularity conditions are satisfied, we finally get a solution of the second equation in 13 as given in 15. Then the solution of 12 can be written as indicated, where s is an arbitrary complex function or real variable, and h is a real arbitrary, strictly monotonic, and continuously differentiable function or real variable. The next table shows some examples of one-parameter reproductive families, together with their characteristic function and their associated s and h functions. Note that this table contains interesting examples of reproductive families of distribution, such as the binomial, the negative binomial, the gamma, the normal, and the chi-square families. In this example, we extend the previous problem to the case of biparametric families. Thus, we need to solve the functional equation in 16, where the characteristic function f is a complex function. The function g is a real bidimensional vector function of two real bidimensional vectors and shows how the vector parameter of the sum can be obtained as a function of the vector parameters a and b of the two random variables being added, and the asterisk denotes the complex product. Under some regularity conditions, the general solution of equation 16 is 17, where a1 and a2 are two arbitrary but independent real n-vector functions. The reader should check that 17 is in fact a solution of 16. The next table shows some examples. This table shows the interesting examples of biparametric reproductive families. Our last example refers to bidimensional densities with linear regressions and conditional distributions in location scale families.
And finally, I am going to explain you the case of linear regressions with conditionals in location scale families. You know that the joint density is the product of the conditional given and times the marginal. In this case, the conditional of x is given y, but we can also use the conditional of y given x and then the conditional the marginal of x. So you have a functional equation like that. You have an equation and you have four unknowns, f, g, h, and k, and you can solve that.
In this example, we characterize all bivariate distributions with linear regressions and conditionals in location scale families, as in Arnold, Castillo, and Sarabia, 1992. In other words, we solve the functional equation in 18, where k and g, f and h are the marginal and the conditional probability density functions, respectively. A, B, C, and D are arbitrary constants, and we have assumed that sigma 1, sigma 2, sigma 3, and sigma 4 are finite and positive values. Our problem consists of finding all functions f, g, h, and k that satisfy 18. We distinguish the following cases. Case 1 corresponds to b equal to d equal to 0. In this case, equation 18 can be written as in 19, where c is a constant. Thus, we have the trivial solution of 18, that is, the independence model. Case 2. Case 2 corresponds to non-null b and d. Then 18 can be written as in equation 20. The general solution of 20 is the one indicated in this slide, which shows that only uniform, exponential, and normal families of distributions are possible. This table classifies all solutions depending on the values of a1, a2, and b1. Cases 2, 4, 6, and 8 correspond to normal bivariate models. Case 1 is the independent uniform model, and case 7 is the bivariate independent exponential model. Finally, models 3 and 5 do not lead to a bivariate distributions because of the incompatibility of ranges between conditionals and marginals. No other bivariate distributions exist. In this lesson, we have given interesting problems in statistics that can be solved with functional equations. We have seen that the maximum stability and the reproductivity can be converted into functional equations that provide the set of all reproductive families. We have also seen that functional equations play a very important role in conditionally specified distributions. I invite you to follow the next lessons dedicated to fatigue models, in which we show how fatigue models can be generated based on their properties, that is, with no arbitrary assumptions.